Okay, thank you to be here for the lecture of today. Do you remember last time I introduced the concept of the discretization? Not only, I think we stopped here. I don't remember well, but in any case, it makes sense to restart here from here because this is really the first slide in which yeah, the Kalman filter is somehow characterized. Nevertheless, I would like to repeat, just with words, the motivation, or at least the most important motivation. Do you remember the simulation using this kind of Lundberger-Kalman filter? Now I am speaking about kind of Lundberger-Kalman, excuse me, Lundberger observer, Lundberger observer. Because also in the Lundberger observer, we have variations. No? But anyway, didactically, the idea was to introduce the concept of observability, detectability, an observer, and so on, in order to show you what the Kalman filter in terms of observability, excuse me, in terms of an observer, in terms of application in the context of an observer, can be done. Do you remember, if I add the noise in the measurements, or noise in the data which I receive from my application, from health institution about the number of infected people, from a bank which give us, I don't know what, error somehow in the data. We have some problems in the let me say in the observation, if you want, in the estimation. Please pay attention. Observation is not exactly estimation, even though very often we use these two words with the same meaning. Observation means exactly what I told you last time in the context of the Lundberg. Basically means that I fit, let me say so, the state of a system could be asymptotical, could be finite time. In this course, we will see just asymptotical fitting, asymptotically observation in this sense. Also, the Kalman filter, this Kalman filter, the Kalman filters, which I will present in this course, they are asymptotical estimator. Why are you speaking about estimator now? You can say also observer, because when we speak about estimator, we speak about an optimal observation, an optimal fitting. We will see also today what I intend. Yeah, this was one of the most important motivation, together with, do you remember, I simulate, again, the noise in the measurements. You can find my study, but also I simulated an error in the knowledge of the system. You remember, I put the matrix B and a factor 7, and I put an exaggeration, but if you look at home, the real, yeah, the real number was 1. If you put 1,1, you can realize it's relatively small, but in any case, bias. Now, I told you that the Kalman filter can try to manage. Can try to manage means it means that we have to find a compromise. We have to be able to first of all to implement this, to understand, and he tries to optimize this situation in which we have some let me say uncertainties. This is the motivation which I introduced last time. We have also other motivation, but let me remain on this most important, which characterizes at least let me say our course. But during the semester, during the application, I will show you also other aspects. These two aspects are the most important. Notations. Yeah, A equal AK, because very often in Kalman filter, we assume that the model is already, if not, we have to do the discretization, as I told you. But in the algorithm of the Kalman filter, we are always in the presence of discrete structures. This means A is a matrix which is discretized. You remember this? I put it here, this stupid example of the stupid, so stupid of the DC drive, no? Characterized by AK, BK, C, and D. We will see during the semester that also the output equation, the equation of the measurements, not necessarily consist of matrix C and matrix D, could consist also more complex structure, in particular if the system is nonlinear. In the second part of the course, we will see also this aspect here. This means not necessarily C and D are constant matrix. In this course, I will consider all system. I have nevertheless also some examples with D not zero for didactical reasons. But in the project, we can consider also D not zero. About D, I will tell you a little bit later what the meaning is. I think one example I already told you. I don't remember. But it's not so difficult to implement in the project because D somehow must be known if D is present. Present is always present, but we can see until now we have seen just D equals zero, but not necessarily at zero. Nevertheless, I will tell you a little bit. Again, A equal AK. This means when we see A in the Kalman filter is discrete, the same concept for B. Yeah. We can see that we have the same element, 4 elements, as in the Lundberger observatory. Remember the state vector you can see here. Here is the model. Here is the model characterized by the X as a observed vector. We can see X hat. Here we have a without hat. I will clarify why the difference between at and without at. I already told you a little bit. Anyway, the state vector X characterized by n elements and components and states. UK is the input. The dimension is L. We will see a little bit more in depth to what I am saying with this L dimension in one minus A as the matrix n times n. We have seen also in an example 2 times 2 if the number of states equals n. B is the input matrix, as we have seen in Lundberger observer, which is characterized by n row and L column. Now we can understand a little bit better why L is the dimension of U. I mean, U is, in our application, we will consider just L equal 1, just one input. But if you want in the project, we can consider in the application, we have also more than one input. If the system consists of more than one input, if you consider a 3-phase model, we have 3 inputs, L equal 3. But it's clear that the matrix B is n, the number of row equals the number of states, we can see here. Of course, if we have here 2 inputs means U1 input in the first row, and the second row, U2 inputs. The synchro motor, I don't know if you know what is the synchro motor, is with 3-phase motor, better to say. We have 3 inputs, this means we have 3 rows. This means the matrix B consists of 3 columns. Therefore, B is characterized by dimensionally n times L. L is the number of column, n is the number of row. But you don't have to learn this. It's intuitive. I try to explain a little bit the nomenclature. Very important. Now, please pay attention here. What characterizes the Kalman filter, at least until now, or what is the difference between the Lundberger observer and the Kalman filter is exactly this, let me say, row here, in which in this row we introduce a new concept, system noise. But now we can understand the meaning of system noise because you remember I told you everything which I don't know about the system, everything which is not clearly defined, could be the parameter as last time, Remember, in the matrix this was, I think, 0, 1. I put 0, 7 just to show you with an exaggeration what happens if I don't know the parameter. Try at 1, 1. We can see that nevertheless the observer does not converge. Will converge, but with a bias. If I know perfectly, we will converge asymptotically in this kind of observer. We have a kind of observer also with converge. We have a kind of observers which converge in finite time. I meet exactly in time T1, time F, the value. But we don't have time to speak about that. But it is also in our group, but this is a little bit more a topic for PhD students. Many applications in this context here. The students sometimes ask me, but if the convergence, if the estimation and the sense is asymptotical, this means I will never achieve the value. Yeah. But in application, very often we apply the asymptotical observer, Kalman filter, one of them, or at least this form of Kalman filter. We have also infinite time. Because the implementation is easier. The implementation, but it's not the problem of easier. Very often we are looking for, at least in engineering fields, an algorithm which should be, or it is suitable to be applied with the minimal number of calculation load. This is the case if you compare finite time observer with asymptotical observer. And very often the problem of the asymptotically convergence is related to the model. In the real case, nevertheless, we have a convergence in finite time, or let me say the error can be, this is mathematically proved, can be reduced, or better to say, can be speed up as we want. This means very often we apply an asymptotical observer. Okay, what is the system noise? The system noise we can see is characterized by a vector with the same dimension of the states, or the state vector. N, and this means this vector here consists of n component. All signals we can see are sampled. About that, I told you what I intend. With a picture, I think I drew, I graphed. You remember this stepwise constant approximation of the continuous system. Meaning, system noise means everything which I don't know about, let me see, in a word which is reflected here, about the system. Everything. Now we will see that this everything aspect should have some characteristics. Or at least in this course, we will see the family of the Kalman filters with specific characteristics. We will start with this because didactically it's suitable to start with this basic, but not only. Very often we applied also in the praxis, in the practical application, in the applications, this kind of Kalman filter. I will show you in one of the next slides. In the second table here, the notation is changed with respect to the Lundberger, because, or at least we can see also here maintain A and B, maintain X and U, but here changed in the Kalman filter. Z was in the Lundberger Y. Do you remember Y, YK? I think is also here. No, I put here the current. Yes, is Y, but the YK. The output. Probably in the previous slide we have a Y. Here, exact. Basically, what they are measuring, it's it. We will see that this output equation this we will see during the course, could be called also output equation, because not necessarily Z is directly what we are measuring, but inside the output equation, we have something which measures, but Z or the output equation could be also a part of the model, a part of the model. I will show you some examples, because sometimes we have the possibility to represent the model in the dynamics part, but also in the output part. We will see. K in the Lundberg was C in matrix in the Kalman filter. Not always. In some books we have also different notation, but this is the most used, or at least in this literature. This, I think, at the end of the lecture of today, at least in a part of this paper here, you can read. This means you can download. The one I told you is somewhere here also. Yeah. It's a very interesting introduction, very compact introduction. Of course, it's good for people who already know a little bit Kalman filter, because it's so compact that it's extremely difficult to understand without. Yeah, it's possible, but anyway, it is difficult to say without an introduction, even though it's an introduction. Otherwise, you can read directly the papers written by Kalman. This is more difficult, in my opinion. I put, I think, in the first slide some reference, or at least one. I don't remember how many I put there. But after this course, believe me, I hope that you will be able to not only to read the paper related to this kind of Kalman filter. We will characterize in a few minutes which kind of Kalman filters we are speaking, but also different Kalman filter. Please, the dimension before speaking about the last row, which is the most important. We have M dimension. This means until now we have seen just one output. I don't remember if I told you about it, but we can have M outputs. I can measure also more than one output. The same thing I can say for H, which consists in this case of M row and M states that we have seen also from here. No? Here we measure one output, the current, in order to estimate current and velocity, particularly the velocity, which I don't want, which I cannot measure. We can see that C or H, in this case, we have M equal 1 row and 2 column, because the state equal to, no? M times N. But Z, the dimension of Z, equals M. The number of, let me say, elements a little bit too generic, state, the number of states which I am measuring. Very important. The last line characterizes the output now in the context of the Kalman filter, which can see another noise. But now we will, the lecture is known as measurement noise. We will see that it's not necessarily just a measurement noise. Could also represent a system noise in case in the output I have the model of the system, or the part of the model of the system. There's a little bit an advanced application of Kalman filter, but we have it. M dimension, because depending of the number of sensor. If you want, M is also the number of sensor. This means the variables, state variables, which I am, very important, state variables, which I am measuring let me say in output. Let me say. Okay, let me see if I forgot to say something concerning this slide. I don't think so. Let me now go ahead. Before characterizing the Kalman filter, let me show you a little bit the structure. This slide I don't like much, but I hope that I try to explain, and I hope that at end, at least an idea about the basic structure of the Kalman filter, any kinds, any kinds of Kalman filter. Look, it seems to be that the Kalman filter consists of two steps. Please pay attention. Within a sample time, inside the sample time. Now, about that, I told you what a sample time is. Within a sample time, we do what the Kalman filter does, and a prediction step. In some books, you can find a priori approximation, sometimes a priori estimation. You can find many different notation, a priori, an a priori action. Of course, is an approximation. And then, in a correction step, which you can find the literature with the nomenclature a posteriori correction. In some books, also a posteriori estimation. Correction, I like mine a little bit better. This everything inside, I would like to say, in sample time. Two steps. We can see directly from here that the Lundberger observer is not exactly organized in the same way. We don't have these two steps, if you want. We have here an important word, optimal. I already told you this is an optimal algorithm, and I will show you what is the meaning is. Let me go fast ahead, really fast, because the idea should be nice if I am able to tell you about an application. And then it could be that we will come back on some mathematical aspects. Look at this. Equation 1. Equation 1 is quite similar. What I already told you, for instance, here. At least, if you consider. Oh, here. Here is a little bit strange because here, do you remember, I told you that this expression here is the general discretization of the matrix A, which I already told you what is the matrix A, is the continuous matrix, or better to say the matrix which characterizes the continuous form of the system. Anyway, this expression here, identity matrix plus A multiplied TS, represent this AK. We can see a little bit also here, no? This matrix here can be seen as an identity matrix. We can see 1 here, and 0 here, 1 here, plus the matrix T, the matrix A multiply T. But we can see everywhere is T, and what is A? Yeah. Last time I told you that. You don't have to learn this because MATLAB does for us these calculations here in the context of matrices here. Anyway, this expression here is exactly this expression here if I don't consider this vector here. The meaning is of the equation 1 is, let me say, the true of my real world. This is the truth in the context of Kalman, of course, in the context of Kalman, because now we will characterize the vector W. This is the truth in the context of Kalman because this expression here, this vector here, we can see here a little bit that consists of a distribution of is in noise. Is basically we can see this notation means is expressed here and is in a process noise characterized by normal probability distribution in which we have the mean value 0 or expected value 0 and characterized by a covariance matrix Q. About the covariance matrix, probably you are data science, you know better than me, but I try to express the meaning of this a little bit intuitively again. But I would like to insist on this concept here. W is characterized in this kind of Kalman filter, or the Kalman filters, by a noise. This means a random variable, which have a distribution, normal means Gaussian, with expected value 0, characterized by a noise covariance matrix. Variance we know from school. Covariance a little bit more unclear. I try to explain in a matrix. I try to explain a little bit later. Keep in mind this normal probability distribution, Gaussian. We have also Kalman filters with non-Gaussian. I don't have time to tell you about that. This is the most applied, the most important, because very often we know that in nature, even though some phenomena are not Gaussian, but through repetition, this not Gaussian distribution tends to Gaussian distribution. But in general, the Gaussian distribution is the most natural one. But not all distribution or not all phenomena are Gaussian. But let me say the most natural, but not all. This means we have also Kalman filter with different distributions. Very important is again, why this is the true? It's the true because Kalman says with xk without hat. Now we will try to understand. Here's a little bit in general. Here's a little bit more clear. A little bit more clear because we have a real system. And hat means approximation. About the approximation, I told you the meaning because it could be that the real system consists of inertia or that the resistance R. Do you remember it changes? In the real system, we have 1 divided L. No? 1 divided L. TS is not there. Also, this is an approximation. Before going ahead, I would like to show you, look at this expression here and look at its continuous system. Look, here I didn't put hat. I didn't put hat. You remember, I simulated, I don't remember, not the system, but it's as if I changed the value of L. Do you remember? I had 1 0, I put 7 zeros, something like that. I don't remember what, or probably the input was there, but I don't remember. Here, the meaning is, here is the system which I know perfectly. This means I don't need to put hat. Here, I put hat, even though you can find the same parameters, but in any case, we have a TS, which is not here. Clear, no? The difference is just yeah, this is the continuous system, which I assume to be true. And here, we have a system which is different because it's discretized. For instance, we have TS, which is on top of that there, but also the structure of the system is different. This structure here is came from forward Euler. I will sketch a little bit also backward Euler once, but a little bit more complex. We did in a project with the Rolls-Royce Research Center in Friedrichshafen in Germany, in which we applied the backward Euler. I will tell you when we can apply forward, when we can apply backward. We have also Runge-Kutta, probably you heard about that. Runge-Kutta method, Euler method, many methods if you open MATLAB. In any case, this is not the true. This is our representation in terms of discrete form, even though assuming that I know all parameters. We have a mismatch between what I am represented here and the true, if this is the true. This means, coming back theoretically on this equation here, Kalman say, what is the true x without hat is what I know plus what I don't know. Assuming that in this element here, I will include parameter which is not exactly uncertainties due to the sample. Assuming that I can say this is a tautology. I know the word tautology. The true is what I know plus what I don't know. Okay, I cannot tell. I mean, in a system, in a world in which everything is split between what I know, what I don't know, of course, I can represent the truth. The same thing for the second equation. We can see that is characterized, I add to my original structure of the measurement. Let me speak about the measurement. We will see that could be also more complex, this output here. In the same way, the error which I introduced with the measurements. The instruments, or the instrument, if I have just one, does not measure correctly. I have some noise, I have some interferences, or the data which I receive from the source is corrupted by I don't know what. Again, this V represent the errors in terms of noise, but again, this V has the same characteristics, the signal here, the probability distribution of V is characterized in the same way as the probability distribution of W. We can see here. It's again the normal distribution with expected value 0, characterized by variance R if I have just one variable, or in a matrix R if I have more than one variable. Matrix, the name of matrix again is covariance matrix. Why covariance? And then we will go ahead. Variance is clear, no? Intuitive. You know what is the variance. So we have a Gaussian, more or less, sigma, sigma square, no? The variance. Well, sigma is the standard deviation. Anyway, an uncertainty. It's characterized by an uncertainty. If I have a random variable, we have this. In this case, is also Gaussian. But of course, if the system is characterized by interactions by more than one variable, it is characterized. Otherwise, we cannot apply, we cannot implement an observer. If you don't have connections, if the variables are isolated, no connection, no observability. Do you remember this concept here? This means the idea is to, in order to describe in terms of uncertainties the system, of course, it is not enough just to speak about the variance for each state variable, but we have to speak about the interaction, the variance of the interaction. I show you better in 1 second, even though I don't want to insist on this mathematical aspect. Here, I summarized the characteristic of our Kalman filters. We have these two variables, W and V, are independent. We can see here. This means they don't influence each other in this sense. They don't influence each other. White noise, I don't know if you remember, the white noise is the noise within a contrast, constant spectrum. And with normal probability. This is the hypothesis which allows now to show you quickly the five equations. Look here, I put it again. The definition of the covariance matrix. If you remember a little bit the statistics concept, expected value in form of mean value, then we have the covariance matrix, Q, which is G multiplied G transpose. I would like just to emphasize, look at the definition a little bit at home, but it's quite clear from this last equation here, the interaction between two different, if you consider n variables and more complex, it's more complex to see, but in terms of two variables, at this moment we consider just a system with two variables. We have basically the variable characterized by I and the variable characterized by J, and we can see how we can define let me say, if I not equal J, let me say the not diagonal elements of this matrix here, in which in the diagonal element we have the variance of each variable. Look at these four elements. The variance which characterizes the uncertainties of the current, and here the variance which characterizes the uncertainty of the omega. And here velocity. Here we have the interaction between. This means if I have an uncertainties in the current, what is the uncertainty in the corresponding uncertainty in the velocity and vice versa. Let me just let me say, recall this concept here in accordance with the definition here, which is always in a quadratic form. I don't know if you remember. From the variance is quite clear, no? Because we have an up to, excuse me, a square if I collapses in J. About this slide, I don't want to tell you more because we will see that the definition is important in case for some particular applications, but basically Kalman filters, how possible to say, assume this, or at least in our at the beginning in our lecture, we assume that we know the matrix Q or the matrix R. Of course, these assumptions must be discussed in depth at the end of during each applications. Excuse me. Let me see if I forgot to say something. In accordance with the definition in a symmetric matrix, define positive matrix, we can demonstrate because G multiply G transpose. If you remember a little bit math, is a positive defined matrix. This means the determinant is positive, is invertible, is symmetric, and so on. But about that, it could be that I have time to go back on some mathematical aspects. Of course, is the Kalman filter which we are considering now. The interaction between the uncertainties, if you consider the current and velocity, between the states, the two states in our case. Look, now we will present the 5 equations. This is the equation, the first equation, which I called also in some books as I say equation A. Equation A. Look at this equation here. Before speaking about a priori error and a posteriori error, this equation here is we know a little bit this equation because somehow it's quite similar to this one. We have nevertheless a small difference, which nevertheless makes something. It deserves this difference to be discussed. We have in the other equation up to minus. Look, here we have x hat equals a or the ak, now it's the same, we have seen, multiply x hat, k minus 1 is also there, plus b or the bk, multiply the u. Look, uk minus 1. It's exactly the same also in terms of Pedix notation, k minus 1, k minus 1. The unique difference is this up to minus. This means that this variable here, the unique difference, let me explain better. This variable here, x hat, independent of the index, is clear. Somehow is the previous value. No? K minus 1, do you remember I told you many times? Is the previous with respect to k. Easy to understand. This is the past. This is the present, for instance. But here we don't have minus. This is a big difference in the sense, or then a difference which deserves to be discussed, because this minus characterizes exactly this equation. The name is a priori estimation of the state, because the a priori estimation of the state needs the previous variable, but it's not exactly the same. In fact, we will see that this x hat without minus came from the correction. This means from a posteriori step. Remember this, we characterize. This means we can intuitively understand that now this scheme here, where is it? with this interaction, we can intuitively understand that the prediction step needs, let me say, or is constructed, let me say, together in the sense depends on the correction step. Basically, this information is going, we will see in detail now, in the correction step. Come back for the next step. And in the meantime, I produce an output. This is a little bit, it's not so difficult at this point to explain. It was difficult to explain this concept, but now it's quite clear. No? I reused what I obtained. In the meantime, I produce the results for the next prediction state. If you want, you can read this. This is the next prediction state, which depends from the preview correct state. Somehow what I know, but inside the Kalman filter, because we have this loop already here, somehow present. Now, makes sense to speak about this a priori. It makes sense. This is my way to explain this information here. The first part of this line, which we can see in a priori error estimation, and then a posteriori error estimation. Some books, you find correction, but don't care about the notation. We can see here that this a priori error estimation is defined, has a difference between the true. I put here in this form here because it's the true in the sense of Kalman. It's the true in the sense of Kalman. The true does not exist. But Kalman says the true is what I know plus what I don't know. Minus this a priori estimation of the error. No? Yeah. Of the state, excuse me, of the state. Clear, of the state. This is the definition of a priori estimation. The definition estimation, the error estimation. A priori error estimation. Here, the a posteriori error estimation is defined, again, the true, minus this xk hat, which at this moment is not clear what is, but graphically, it is here. When I finished my process, or my process within the sample time, I have xk hat here, and here this xk hat becomes x hat k, which I have here. This x hat k becomes here x hat k minus 1 for the next step. I will show you exactly with the software. I don't know if it will be possible today, but starting from next week, we will concentrate much more energy on the software implementation, because it seems to be quite, not only difficult, but quite abstract. But with the implementation, will be clear, a little bit more clear, I think. And then I hope to come back a little bit on the theory. Let me try at least to conclude this structure. Look, we will see in detail what this is in a few minutes. Look at this equation. This equation is the second equation. No, this is the true. Excuse me. This is the true. Again, I repeat it for you. What is the true? I told you what I know plus what I don't know. At least we can figure out something like that without hat, because hat in any case represent an approximation. Could be just a model. This is an approximation using just the model. We cannot see here minus, just the model. This means this signal here is exactly this signal here. The difference is just that this is the previous. The difference here is a little bit more because this signal here came from the correction. It's the previous, but through the correction. Show you a little bit better. This is, I repeat it again, what I already told you here is the same. In order to insist on this. Look at this equation here. Now I try to accelerate because the idea at least to conclude with the 5 equation. This is the equation number 2. To demonstrate this equation here is extremely easy, but extremely boring. Next week, I forgot today. I will bring a book, a didactical book on Kalman. You can find thousands books on Kalman filter. Here I have the demonstration. I have the demonstration of this. Boring, but we will see later. We have another demonstration. Oh, this really, I didn't put the calculation, but I will show you next time with the book, because the idea is to get the meaning. Also here, the idea is to get the meaning, where this equation B, the second equation, come from. It seems that once I defined here the a priori error, the a priori estimate error covariance, which is defined with the expected value, let me say, here we can see as the scalar product between the column vector of the a priori error and the row vector of the a priori error. What is this matrix here? Is the covariance matrix of the a priori error, which we have the variance of the error a priori calculated for each variables, and it's their interactions. It's important, this matrix here. Yeah, theoretically, yeah. Practically, we will see that the Kalman filter is able to calculate alone, thanks this recursivity. Again, I can define in the same way in a posteriori estimation error covariance. In this case, as let me say, scalar product of the product is the product between, as I told you, this is the column vector, this is the row vector. The product between a column and a row is the matrix. I don't know if you remember math. In which I repeat it again for you, the definition. Xk hat minus and xk the true. Now, this equation here came just applying the definition. I show you the calculation without insist on the calculation itself, themselves. Of course, considering this hypothesis here, which is summarized here. Look, this means starting from the definition of pk minus, replacing xk, we can see here. This expression here is xk. If xk is this here repeated, then I have xk hat minus, which is here, with minus here, this minus here, multiply everything, multiply this. Believe me, if you do this boring calculation, multiply, apply the distribution of the multiplication, really, believe me. And look here, for instance, we can see very well that here is exactly P, pk, in accordance of the definition. If you do again the multiplication, this multiply this, then we have the expected value. The expected value of a matrix, if the matrix is constant, in the matrix itself. Let me see if you can see a little bit. Yeah. If you do the calculation, we can see that this is exactly, if I apply the expected value of A is A because it's constant. The expected value of this element here is P at step k minus 1. Believe me, it's extremely easy to do if you remember a little bit some knowledge in statistics. And of course, applying some property, that's the noise, W and V are independent. This means the expected value of the product is the product of the expected value. Here we can see that the expected value of this variable is 0 because the hypothesis of the Gaussian is the expected value is 0. The hypothesis of the expected value of this matrix of this product here, W is the noise, system noise is Q as in the definition, Look at how we obtain this one. It's just boring, just in gymnasium to apply the product between, let me say, element, the sum of elements, and expected value of what, of product, independence. Let me go ahead because I would like to. It's really basic knowledge of algebra and statistics. But please, in this Kalman filter, with this hypothesis, this is important because if the hypothesis is not satisfied, we have a different equation and different Kalman filter. Just to fix this a little bit, the concept until now. It could be that we come back on this equation here if I have time, or during the project if we want to do some different kinds of Kalman filter. I don't know, the idea to sketch a little bit what I intend. We can see here, for instance, which I use the hypothesis which I told you at the beginning. And here I use somewhere the independence of the W and V, and here, yeah, again, I have the expected value of the product of this element here. I can say the expected value of A is A. The expected value of this product here is pk minus 1 in accordance with the definition. The expected value of A transpose is A transpose because it's constant. The expected value of the product of variable, if they are independent, is the product of the expected value. It's this basic knowledge of statistics. Now, equation number 3, we are almost ready because the rest of the equations, again, I don't want to demonstrate, but I sketch the idea. Yes, it's important to notice that Kalman put this equation here as a possible hypothesis. He says, we are using a model which is linear. You remember this? Last time, I insist this time, linear discrete Kalman filter. Anyway, last time I told you that this is a linear system. Before last time, I insist this is a linear system. Anyway, at this moment, it's a linear system. We will see after some exercise with matrix simulating also the nonlinear variation of the Kalman filter in terms of extended Kalman filter. Extended Kalman filter is in a way to represent, in the context of Kalman filter, a system which is nonlinear. We will see why extended the name. We have also another big family of the family, yeah, you say family, with the same hypothesis. The name is unscented Kalman filter. It's a little bit different, but it's based on extended, if you want. And then we have ensemble Kalman filter, many names I also forget, because the Kalman filter is characterized by these 2 steps. In this context here, you can invent your Kalman filter with different hypotheses, with different corrections, with injection of signals and so on. This means if you look in the internet, Kalman filter, you can find many different structures. But anyway, with this hypothesis here, excuse me if I go up and down, I lost a little bit. Yeah, with this hypothesis here, we have 2 kinds. Basically, I would like not only, but the most important are with 2 kinds of Kalman filter in terms of nonlinear structure, extended and ascended. Remain here in terms of linear. Linear means linear model. If we have a linear model, in this sense, if we have a linear system, a real system, because the model reflects the description of the reality. Kalman says, the system is linear. Why not to think about an estimation of the true, x without hat is the true, as a linear combination of what? A priori knowledge plus a correction between what I am measuring and what I am in mind, in my a priori knowledge, multiply in the factor. We change over time. Time in our case is a step. No? Inside the microcontroller, inside this Kalman filter is a step. You remember this? this approximation of the system using the sample time, which basically generates yeah, step, at least in our representation forward, also in backward, stepwise constant approximation of the function. In our case, we have also different way to represent. I don't know if you remember this trapezoidal Tastin method. We have also other many methods to approximate. I told you in terms of discretization. Assuming that this is my correction. I mean, what I know in advance, or using eventually the previous correction, because you remember here inside, we have, of course, our pre-knowledge, but also the correction of the previous state. Pre-knowledge is not wrong. Xk hat minus, I insist in order to understand this. We can say pre-knowledge because A and B is our a priori knowledge. This here, of course, depends on the correction, but it came from k-1. This variable came from k-1. I consider a priori knowledge somehow. Also, this is dynamics, but in any way, we say a priori we can see in the letter estimation of the state. What I knew at least from the state before. State before is quite clear. And A and B, that's really what I know in advance from my knowledge in terms of, do you remember I told you at the beginning of the semester, Newton laws, Kirchhoff law, in accordance with the system which I have. Also different knowledge if the system is a chemical system or economical system and so on. It's interesting in the possible interpretation of the equation C, because it's basically, again, a linear combination of what a priori knowledge, what I know, could be also dynamics, because it's improved through the correction, plus, this is interesting interpretation, because it's the difference between my direct experience, my measurements, what I perceive, minus what I knew in advance. Basically, I knew something, but Kalman structure say I am able to change my idea, my representation of my reality in accordance with my experience, what I measure. But I weight this. Very important, because now we discuss this. Today I will not be able to do the simulation, but I promise next time just simulations. I will weight this new thing using a matrix we will change over time. And this matrix here somehow represents the a priori, it depends on the a priori knowledge. This means I am free to, I am open, better to say, to improve my a priori knowledge in accordance my experience. My experience is what I perceive minus my prejudice. Let me see. What I know in advance. But I will wait with my previous knowledge, because we will see that this can be seen as a function of my previous knowledge. In a semiotic concept, do you know the word semiotic? Semiotic is the science of the symbols. Semiotic. What does the symbol means? We have the product between what I know in advance plus the difference from my experience and what I know before. The product in math means meeting. What is the improvement of my knowledge? The knowledge is this one, a priori. It happens when my a priori knowledge meets my new experience. This is a possible interpretation, a philosophical one. Semiotic, if you look in Google, probably you know a semiotic. The words, the science of the symbols, the meaning of the symbols. The product in math means could mean to meet. We are close. Let me go ahead. The name is innovation of this difference, or in some books, if this is what I perceive, the difference between what I perceive is my a priori knowledge is my experience. But anyway, this is an impossible experience. Let me skip this boring thing, even though important. We'll come back by this expected, but this statistical part. Let me because I would like to conclude with the 5 equations. Look at this. If you consider now the a posteriori covariance matrix, which is basically, let me say, the variance covariance, if you want to be precise, but at least in the diagonal, because we are speaking about the trace. Look, the trace. Do you remember the matrix, the trace of a matrix? The sum of the diagonal elements. If you don't remember, that's not matter. I tell you. The trace is the sum of the all diagonal elements. In our case, now we don't need to recall the covariance, because the trace of the covariance matrix is the sum of the variance. Now, the variance is a common concept, no? The variance. We can calculate also in high school. Now, if you consider this trace, this means the sum of the variances. This means the sum of the variance of each variable. This means somehow the sum of the error of all variables. And let me skip this thing, because I would like today but in the book which I will bring in the next week, we will see it's not the goal of this course. The calculation is extremely boring, not difficult. Believe me, not difficult, but boring. What Kalman does now is to calculate the minimum of this trace with respect to kk at each k. This is the idea. Assuming the equation C, this concept of the correction of the estimation, a posteriori estimation, and so on, what I know in advance plus my experience weighted by my a priori knowledge and so on. This is now, of course, an assumption. And he demonstrates, next week I will show you the calculation, but just passing through in the book, because it's 3 or 4 pages written very small. I didn't put here at all this. Basically, what is the idea? If you put here xk, exactly as I told you until now, xa was far away. Where is xk? This xk is this one. And if you put here xk hat, which is the matrix C, here and here, if you do this product as before, do you remember I told you when I calculate the matrix, the equation B? Look, this expression here depends of k, because this expression here depends of k. K. If you do this boring calculation, this kk appears everywhere. It's not difficult, but then you do the expected value with the hypothesis, which I told you, and then you do the derivative, and you will find, I didn't put also here because it's really boring, but it's not difficult. It's a derivative with respect to kk, symbolically. You will obtain this result here, in which we have the minimum of the sum of the variances of each variable, of each state variable. This means the minimum of this, let me say, errors, or the sum of the errors, is here. Is here. And this is the KK, which realize the minimum, let me say, of the sum of the error. And at this KK, we have the function PK, which we want to minimize, equals this one. Believe me, I showed you last time quickly the calculation you don't have to learn. It's irrelevant. But the idea where these two final equations come from is important to have at least an idea. Now, the last question, which is expressed, which is here, we will discuss those things. And next week, believe me, I will show you the simulation I upload for you, working files for the Kalman filter. But now we have the sum of the, I don't know if the answer, no, it's here, I think it's here, yeah. Yeah, we have the sum of all of each, in the sense, variance. But we can demonstrate here, we have also the reference in which that this KK minimize not only the sum of the variance of, not only the sum, but also each error separately, because we have a form of orthogonality, no? If the system is linear, with the hypothesis which I told you, Gaussian and white noise. This means not only the sum, the minimum, not only the trace, but each variance. This is demonstrated later. We can see, if you remember, the first article of Kalman is 1960. And here we have a little bit later the formal demonstration. I don't remember if we have also something before. Yeah, probably is more advanced. But in all of these three, I have to be more precise in the literature, because I did input, but it's not so relevant. I mean, you can find, because these three papers we can see here I cited in one. Now, this means you can find what should be better if I am a little bit more precise, directly write this one. I don't remember if you have also something earlier, but in any case, here we find everything about this aspect in which you don't minimize just the sum, but minimize each error separately. It's the same. This solution here realizes the minimum of each variance. This means minimize the errors, the estimation error for current and the meantime velocity, if you consider our example. If you think about, I am concluding 1 minute, Q and R, because do you remember I told you that Q and R represent the uncertainties of the system, knowledge of the system, and R represent the uncertainties related to the measurements or the output equation. This is extremely important because it is extremely difficult to estimate, in particular Q. R, sometimes the sensor, if using the sensor, is characterized by an error, or we can, through measurements, guess. Of course, we cannot be precise, but we could have an idea about R. About Q is more difficult. But in any case, Kalman, I met once Kalman, Professor Kalman, in the conference, not personally, in the conference. I remember one question, not from me, from a professor. I was very young. In Italy, I met because at the end of his career, he was professor in ETH Zurich in Switzerland. A professor asked him when Kalman filter does not work. Because it seems to be that, believe me, Kalman filter is applied everywhere. Everywhere. I work with Volkswagen, in ABB, Kalman filter is everywhere. So, yeah, very often used. Because it seems to be, the professor asked him, it's applied everywhere. It seems to be that it's able to solve many problems, or almost all problems of estimation. And Kalman answered, so it's strange for a professor to hear this question, because should be known that the Kalman filter cannot work. Kalman filter says Kalman doesn't work. The reason is that it's not a theorem yet. I didn't present it as a form of a theorem, but the hypothesis is that we have to know perfectly Q and R. This is impossible, but we can estimate. This means doesn't work is missing an emphatic answer and a challenging answer to say, please pay attention that we have some limits, and the limits, one of the limits, or the most important limit is the estimation of the knowledge of R and Q, and this means their estimation. Here in my group, we estimate Q and R with different methods. For instance, PSO, particle swarm optimization methods. I don't know if you know. You can use neural networks. You can use any kind of deep learning systems. With the students of data science, very often in this course, at the end, we realize different algorithm to estimate Q and R. This is a very important aspect. To conclude, and then we will recall, I will start with this concept here, but inside the simulations. What about Q and R? Q represent the uncertainties on the error related of the knowledge of the system. This means if Q is very small, means the model is very precise, because Q represents the variance or the covariance of the W. W is the system noise. System noise means what I don't know, let me say so about the model. And this is reflected here, because if Q is very small, theoretically zero, assuming that I know perfectly the system, perfect, the real system, this means Q is zero. We don't have statistical variable. The variation is zero. The Gaussian collapses, and it's expected value. This means K is zero, because in P minus, or at least it's not zero because we have this value here, but it's minimal value. Assuming that's P also zero, and just to understand what happens in the Kalman. It happens that the estimation of the corrective value, which approximate the true, is just the a priori knowledge, because I don't need to correct. Everything is known. This is a little bit the idea. The same consideration can be done for R. R characterizes the measurements. For instance, if R is very small, if you look at at K, if R is very small, we have the maximal value of KK, or the K, let me say. If R is zero, I mean, the sensor doesn't make error. This means the sensor speaks the truth. We can see that the denominator, let me say, of this matrix is not the denominator, it's the matrix. But let me just to give you the feeling. As in the denominator, we can understand intuitively better. It's the maximal value. Excuse me, it's the minimal. This means K is the maximum. I mean, if R is zero, if you consider this expression as a possible denominator, it's not the denominator, it's in the matrix. But just to give you a feeling, the denominator is the minimal if R is zero, or at least decreases. This means K increases, meaning I trust the measurements, because in my improvement of my knowledge, I say what I am perceiving is important for me because it's the truth. K is maximum. This means using Q and R, I can change the performance of my Kalman filter. I can somehow tune, we say, the Kalman filter. Of course, this can be done, use deep learning, use different methods in order to estimate in the best way the value of the elements of Q and R. We will see next week a little bit this aspect here with the simulations. But of course, I leave the estimation Q and R with the project. We did here, I like a lot PSO, variations of PSO, particle swarm optimization methods. Do you know that? But anyway, you can use also deep learning. You can use also any kind of neural networks. The students of data science, not always, but often dedicated the day project on this problem here. We will see a little bit next time and recap on these five equations. I already presented everything. Just a few things. We have to start the Kalman filter with the initial value of x, the error, and the initial, the states, what I think the state is at the beginning had, because the value, the real value, no, God knows, I don't know that. And the error, of course, this is initial value which I have to put. In linear case, it does not matter which I put. I mean, matter, but it matters, it is important, but it's not important in terms of convergence, because do you remember I told you that the covariance matrix is a definite positive matrix. This means the optimization problem, even though I didn't spend energy today, the optimization problem is an optimization problem. You remember the derivative of p with respect to the k equals 0. But you have to say this is a necessary condition, but theoretically it's not enough. When is this enough to find the minimum? If the function is a convex function, we can demonstrate because it's positive, because because it's positive, this pk is a convex function. This means it's enough. It's not only necessary, it's also enough. Excuse me. The derivative is enough and not only necessary. You remember, to find the minimum, we look at the derivative, the first derivative, then we look the second, and the more derivative. Yeah, I didn't tell you about that because pk is a convex function. This means it is enough to do the derivative. This means in the linear case, it doesn't matter which value I put here as initial value in terms of state, in terms of error. Of course, I will need more step to achieve, but we achieved them. Of course, if I'm far away, I need more step. And we can see here the concept here of the recursivity, in which for the next step, xk is equal xk minus 1, or vice versa. And again, pk is equal pk minus 1. This I did insist on this concept here, but we can see here. No? Yes, pk, the value of the covariance matrix, but I need here pk minus 1. This I told you very quickly when I introduced this equation here, that we have a pk minus 1, because what the expected value of the error, a posteriori error calculated at k minus 1. I will come back very quickly next week, restarting from this scheme here, and then believe me, I will simulate. So I will repeat this abstract concept, these 5 basic equations using the simulation. Then we can understand better. I upload the simulation material because it's important for you during the project that you used working files. Okay, if you have question, I'm here to answer your questions. Let me stop recording. And let me see where. Okay, now.